Please welcome to the stage Rohan and Chris from the Turing Roche partnership.
Hello, everyone. So my name is Chris, and this is my colleague Rohan, and we're both theme leads on the Turing Roche partnership at the Alan Turing Institute. We work on a wide variety of different topics, this is a different slides, different order. Starts with this one. Well, that's fine. I will just talk in general, and you can imagine some fantastic slides up here. So we work on a large variety of different topics. So one of the topics we work on in particular is clinical AI. Now, clinical AI, as I'm sure most of you are aware, has got this huge potential to really revolutionize our understanding of medicine, accelerate and optimize clinical decision-making, and really dramatically improve human health. But there are some issues at the moment, which means that very little clinical AI is actually making its way into the clinic and actually becoming reality in terms of clinical practice. And what I actually had originally was a long slide explaining all the different barriers of translation to clinical AI. And I like to categorize them into three main groups. One are challenges associated with the data that we generate. Clinical data is extremely heterogeneous, very complex. The other set of challenges are associated with the models themselves. How do we construct the most clinically attuned models? How do we train them? How do we validate them? But the final and probably most important challenge in implementing clinical AI is associated with the application of this AI. Once we've built our model, how do we get it into the clinic in a usable way? And this is a really important challenge in clinical AI, particularly, because you can imagine developing a fantastic model, extremely well-trained, extremely accurate, but if the clinicians aren't interested in using it or they're not able to use it for some regulatory reason, then it will never actually realize its potential and improve human health. So today we're going to talk about two potential challenges that need to be overcome in the application of clinical AI. And one is transparency, and the other is personalized uncertainty quantification. So I'll hand over to Rohan now, as these are actually his slides, thankfully, to talk about transparency.
I hope your uncertainty slides are there, Chris, later. So I will spend a couple of minutes on the transparency of AI in healthcare and go over a few examples of it. First is hybrid deep learning. That is a combination of data-driven black box deep learning with more interpretable mechanistic models. And this can be done in several ways. Here we have a couple of examples. On the top, we have the example of cell segmentation, where we use off-the-shelf deep learning method to get a rough estimation of cell segmentation, and then use a mechanistic model, which is unsupervised, to segment the more challenging ones, like the overlapping cells in a digital pathology slide. The combination of deep learning and mechanistic models can take various forms. In this case, it is a digital flow model, where it cuts through the overlapping areas at the point of maximum pressure. Just to show another example, the one in the bottom, again, we have a unit-style or segnet-style backbone, deep learning backbone, and then we have level sets to segment tumor regions in lung city. But the goal here is to have an end-to-end method, and the benefit is less need for expert annotations and labels, and have a more interpretable mechanistic side of the overall architecture. Another example, this one being of feature alignment. It is important to maintain that the features being learned by the deep network aligns with clinically relevant features. This can be done with simpler ways like data visualization and heat maps. However, if you do have a few annotations from the clinicians, you can take the difference between the heat maps and the annotations to have an additional error function, which can be fed back into the system to make sure that the AI system is looking at the proper areas of your image. In this case, the two examples being of breast cancer and skin cancer. The last example from my side would be graphical neural networks, where you can a priori decide where to place the nodes of your graphs in a more again, interpretable or explainable manner. In this case, we had a multi-scale graphical neural network, 3 stages. The first stage being the most zoomed in one, where the nodes are actually placed on the cells we are interested in. And then a second stage, a meso stage, where they are clustered in areas of tumor microenvironment within the slide, and a final larger network at the whole slide level, which looks at the bigger picture. So hopefully we have... No.
No, wow.
Well.
Then unfortunately you will just have to look at me and not the slides. Forgive me for that. So the last thing we wanted to talk about is about personalized uncertainty quantification, which I think is an extremely important aspect of developing clinical AI. And to explain sort of why that's so important, we can think about the recent guidance that's come out of the EU AI Act, for instance, which has set out some regulations for ensuring that high-risk AI is developed in a responsible way. And one of the recommendations for high-risk AI, which clinical AI will undoubtedly become, is that you need to have human measurable outcomes to assess the risk in applying your AI to each individual patient. So you can imagine as a clinician, if you have a particular clinical AI tool and a new patient comes in, one of the really important assessments in determining whether or not you can use this AI tool is to be able to assess the reliability of the prediction for that individual patient, because different patients have completely different characteristics, and what might work well for one patient might not work well for another. And so there are many, many different tools in which one can apply in order to quantify uncertainty in a personalized manner. But one suite of tools that we think is particularly promising is called conformal prediction. Now, without my slides and in the short amount of time, I will not go into the mathematical details of conformal prediction, but suffice us to say that in the words of its inventors, Gammerman and Vock, conformal prediction uses past experience to obtain an understanding of confidence in future predictions. And to me, this really resonates with how learning is done through clinical practice. And we're quite excited about conformal prediction as a potential tool for understanding personalized uncertainty quantification in clinical AI applications. And if you are interested, there is a paper that we published recently in Nature Medicine last year outlining how this tool can be used. Unfortunately, I cannot demonstrate it for you here, but if you look it up, it's there. So that is some of the challenges that need to be overcome in the translation of clinical AI. And I think one of the most important points that I wanted to make in this talk is that while there are many, many barriers, currently they're mostly thought about only at the late stage, only at the point where you've developed your tool and you're ready to translate it. And what we would like to sort of encourage is a dynamic thinking about these barriers to translation of clinical AI throughout the AI pipeline. And this will require an interaction between industry, between hospitals, between clinicians, between data scientists, a real interdisciplinary team. And that's something that we're trying to build at Turing Roche. And if anyone is interested, please come find me afterwards, because I can't give you a QR code here right now to discuss this. And thank you very much.